Hello my dear students, today we are going to discuss a very beautiful concept. It is very useful in our regular life as well as for our board of intermediate examinations. Most frequently they ask this question also. It is very easy to learn and understand. So follow my lecture. After this lecture just practice once or twice. I am giving you the notes in the form of a PDF also in our app. You can download that and you can practice. Okay, so let us see what is this. This is from our chapter work power and energy. The question is, define law of conservation of energy and prove this in case of a freely falling body. This is our question. Now let us see the definition of it. It says that the total mechanical energy remains constant when the internal forces doing work are conservative and external forces are not working, or external forces do now work. This is our definition. Let us see what does it mean. It means that the total energy remains constant, means the total energy here means mechanical energy, that is potential energy and kinetic energy remains constant when the internal forces doing work are conservative. Conservative force means if any work done due to any force is independent upon the path followed, then such force is called as a conservative force. If work done depends upon the path followed, we call it as a non-conservative force. First I will give one example for non-conservative force, then automatically you can understand the conservative force. For example, frictional force. Let us see whether it is conservative or non-conservative. If a car is moving from point A to B directly, to move this from A to B, how much force is required? Same car moving from A to some C and then to B, how much force is required? You can easily say. In which case more force is required? Yes, in the ACB case more force is required, because here we have to do work against the friction, opposing force. Friction means the force which opposes the motion. So here we have to do more work than straight away A to B case. So that's why this is called as a non-conservative force. Now let us see about one example for conservative force. If work is done against gravity, if an object is thrown from here to here like this, say this is B, so here when the object reaches from point A to B straight away, or it moves upwards and comes to B, in both the cases same force is given. That's why in this case we call this as conservative force. Here the path is different. But initial and final points are same. So in this case the work done is same, the force used is also same in the two cases. Hence we say that gravitational force is a conservative force. Now let us look into our definition for law of conservation of energy. That is the total mechanical energy means potential energy plus kinetic energy remains constant when the forces applied on it are conservative only. There should be no work due to the non-conservative force. Means if work is done against friction, then law of conservation of energy is not applicable. Is it clear? This is our definition. Now let us derive this in case of a freely falling body. See, this is an object of mass m falls freely from the head, from a certain height capital H above the ground. I call this as point A. After some time it reaches to some point B, which is at a height small h from the ground. Means it got displaced by a displacement of h minus h, because this total is h, this is a small h, this remaining is h minus h. Say after some time it reached to the ground. I call this as point C. Means now the object is on the ground, means it is at a height of 0 from the ground. In these three cases we have to study about the total mechanical energy, and let us see what happens to the total mechanical energy at point A, total mechanical energy at point B, total mechanical energy at point C. Okay, come on. Now first let us study the total mechanical energy at point A. Total mechanical energy at A. At A we have potential energy and kinetic energy. So what is the potential energy at A? mg into h, because it is at a height of h. Now I call this as potential energy at A. What about the kinetic energy at A? Is equal to half mv square. As it is released from point A, at A its velocity is 0, that's why it is half m times 0 square, which is equal to 0. Means the total energy at A equal to how much? Potential energy plus kinetic energy, which is equal to mgh plus 0. So total energy at A equal to how much? mgh. Is it clear? Now note on this, pause and note on this. Now let us study the total mechanical energy at point B. At B, the potential energy is mg into, at what height it is? Small h. So it is small h. Now let us study the kinetic energy at B. Is equal to half m into Vb square, where Vb means velocity at B. Now our job is to find the value of Vb. For that I am going to use a third equation, that is V square minus U square is equal to 2as. From this V means Vb square minus U means initial velocity is 0. So 0 square equal to 2 into A means G into S means displacement. What is the displacement from here to here, A to B? H minus H. That is equal to 2G into H minus H is equal to Vb square. Now can I substitute this Vb square here? So I am going to put it there and let us see what happens. So kinetic energy at B is equal to half m into 2g into h minus h. Half gets cancelled and is left with mg into capital H minus mg into small h. Total energy at B is equal to kinetic energy at B plus potential energy at B. So kinetic energy at B means plus potential energy at B means cancel. Hence total energy at B is equal to how much? mg into capital H. That's all. So it is very clear that the total energy at A and total energy at B are similar, are same. Now let us see the total energy at C. Now come to this point C. Where is this C? C is on the ground. At C, the potential energy is equal to how much? mg into height. At what height it is above the earth? 0. Because it is about to touch the ground. Means almost it touched the ground. That's why it is 0. Let's go to 0. Now let us study the kinetic energy at C. Equal to half m Vc square. So our target is to find the Vc value, same as before, by using third equation. V square minus U square is equal to 2as V means velocity just before touching the ground, that is v square minus 0 square equal to 2g into s means displacement. So what is the displacement when the object moves from A to C? H, 2g into h. So v square is equal to 2g h. Upon substituting this value here, I get kinetic energy at C is equal to half m into 2gh. 2 gets cancelled. This is mg into h is equal to kinetic energy at C. Now our job is to find the total energy at C. Total energy at C means potential energy at C plus kinetic energy at C. Potential energy at C is 0 and kinetic energy at C is mg h. That's why total energy at C equal to how much? Mg h. It is proved earlier that total energy at A is mgh, B also mgh, C also mgh. Hence we have proved that the total mechanical energy remains constant at any point. B means it is an arbitrary point. It could be here, 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 anywhere in between A and C. So it is proved that the total mechanical energy remains constant. So that's all. Sometimes they may ask you that what are the conditions under which law of conservation of energy is applicable. In such cases you have to write the conditions which we have discussed in the definition. They are the internal forces must be conserved, no external force should work. These two are the conditions under which law of conservation of energy is applicable. That's all. Go through my PDF and practice well. All the best.